Hello everyone, welcome back to my YouTube channel. I am Astha, a first semester pursuing my computer science and engineering from Sri Venkateshwara College, Bengaluru. In this video, we will study about the applications of curvature and radius of curvature. So let's get started. In this video, we will cover the definition of curvature and radius of curvature, expression of radius of curvature for a Cartesian curve, and applications. So let's first begin with the definition of curvature and radius of curvature. Consider a curve in the xy plane and let A be the fixed point on the curve. Let P and Q be two neighboring points on the curve such that arc AP is equal to S and arc AQ is equal to S plus delta S. Here, delta represents the small change so that arc PQ becomes delta S. Let xi and xi plus delta xi respectively be the angles made by the tangents at P and Q with the x-axis. The angle delta xi between the tangents is called the bending of the curve, which depends on delta s. Delta xi by delta s is called the mean curvature of the arc PQ. Also, the amount of bending is called the curvature of the curve at P, and it is defined mathematically as limit delta xi by delta s, where delta s tends to 0 is equal to d xi by ds. Curvature, which is denoted by k, is equal to d xi by ds. Further, if k is not equal to 0, the reciprocal of the curvature is called the radius of curvature and it is denoted by rho. Therefore, rho is equal to 1 by k, which is equals to ds by d rho. Note: first, it is obvious that xi depends on s. The relationship between these is called as the intrinsic equation, and s, xi are called the intrinsic coordinates of the point P. Second, we always take the sign of k and rho to be positive. Third, curvature, being the amount of bending, is obviously zero for a straight line at all the points on it. It is easy to visualize that the circle has an uniform bending. So now let's derive an expression for the radius of curvature for a Cartesian curve. Let y is equal to fx be the equation of the Cartesian curve and a be a fixed point on it. Let b x comma y be a point on the curve such that arc AB is equal to S. Let xi be the angle made by the tangent at P with the x-axis. Consider slope of the tangent. Tan xi is equal to dy by dx. Differentiating it with respect to s, we have d by ds tan xi is equal to d by ds dy by dx. On differentiating tan xi, we have sec square xi d xi by ds is equal to d by dx dy by dx dx by ds. But dx by ds is equal to cos xi, and by the definition of d xi by ds, we know it is 1 by rho. Therefore, the equation becomes sec square xi multiplied by 1 by rho is equal to d square y by dx square into cos xi, which we can further write as sec cube xi is equal to rho d square y by dx square. Hence, rho is equal to sec cube xi by d square y by dx square. That is, rho is equal to sec square xi whole to the power of 3 by 2 divided by d square y by dx square. Sec square xi can also be written as 1 plus tan square xi whole to the power of 3 by 2 divided by d square y by dx square. Therefore, rho is equal to 1 plus dy by dx whole square whole to the power of 3 by 2 divided by d square y by dx square. Here we have taken tan square xi is equal to dy by dx as it is the slope of the tangent, denoting y1 as dy by dx and y2 as d square by d square y by dx square. We have an expression for the radius of curvature in a Cartesian plane, that is, rho is equal to 1 plus y1 square whole to the power of 3 by 2 divided by y2. Sometimes y1 at some point on the curve becomes infinity, that is, when the tangent is perpendicular to the x-axis. There, tan xi is equal to tan 90 degree, which is equals to infinity. In that case, we cannot apply the formula for rho in the above form. In such a case, we have to use the formula in the alternative form. That is, rho is equal to 1 plus x1 square whole to the power of 3 by 2 divided by x2, where x1 is dx by dy and x2 is d square x by dy square. We also have an expression for finding the radius of curvature for a parametric curve, but we prefer to use the Cartesian formula itself for finding rho in case of parametric curves also, as the work will be relatively easy. Now, let's look into some applications of radius of curvature. In differential geometry, it is used in Cicero equation, which tells that a plane curve is an equation that relates the curvature at a point of the curve to the arc length from the start of the curve to a given point. Also, it is an equation relating to the radius of curvature to the arc length. Second, it can help to find the radius of curvature of the Earth along a course at an azimuth. Third, besides the radius of curvature, also use these three parts equation for bending of beams. Fourth, moreover, it has a specific meaning and a sign convention in optical design. Also, spherical lenses have a center of curvature. It is also used for thin film technologies and minimum railway curve radius. So with this, we come to an end of our video. If you found this video informative, please do like, share and subscribe to my YouTube channel. Thank you.